Hello, everyone. For today's topic, we'll be discussing on one of the most fundamental topics in biochemistry, and that is water and pH. We need to discuss this topic because 75% of mass of the living cell is water. All of our biomolecules are surrounded with water, and it is important for us to determine and to understand the chemical properties of water and how it interacts with these molecules. Water has also the ability to solvate organic and inorganic molecules, meaning it is considered as the universal solvent. And the reason for this is because water has a dipolar structure and the capacity for forming hydrogen bonds. Later, we'll be dissecting on the properties of hydrogen bonds and how it contributes to being as the universal solvent. Water is also involved in reactant or product formation in many metabolic reactions. And as you can see in our cell, within the cell, it is 75% of water. And we have a lot of chemical reactions and biochemical reactions that will require water in order for it to proceed. Water has also slight propensity to dissociate into hydroxide ions and protons. The hydroxide ions is also known as the OH and proton is the H+. So this property of water is the reason why we have pH or acidity and alkalinity. Water balance, a regulation of water balance depends on the hypothalamic mechanisms that control thirst, including the antidiuretic hormone or vasopressin or arginine vasopressin, which is produced from the posterior pituitary gland. No, it is not produced in the posterior pituitary, but it is secreted from the posterior pituitary gland. The antidiuretic hormone is produced from the hypothalamus and is just secreted in the posterior pituitary gland. Regulation of water balance is also dependent on the retention or the excretion by the kidneys and also evaporative loss through the skin or through other mucous membranes such as the lungs. Another biochemical or biomedical importance of water is that it is involved in nephrogenic diabetes insipidus, in which in this disease, there is the inability to concentrate urine or adjust subtle changes in extracellular fluid osmolarity, which is also depend on water levels inside the body. And nephrogenic diabetes insipidus is due to unresponsiveness of the renal tubular receptors to antidiuretic hormone. Now, our antidiuretic hormone, from the name itself, antidiuretic, meaning it prevents diuresis or it prevents urination. So it tries to conserve water. That's the main function of antidiuretic hormone. Okay. Now, if you produce antidiuretic hormone, okay, but your kidneys do not respond to it, it is like there's no effect of antidiuretic hormone because your kidneys do not recognize them or your kidneys is insensitive to them. So what would happen is that there will be excessive urination. Okay, excessive urination. So you have a water-filled urine, meaning you have a lot of water content inside the urine because your kidneys do not concentrate urine, they do not have the capacity or the capability to reabsorb water, to conserve water. Another biomedical importance of water in pH is that from the property that I mentioned a while ago, that water has a slight propensity to dissociate into hydroxide and ions, we have now the development of pH, okay, which is the concentration of protons in the aqueous solution. And the normal pH of extracellular fluid, please remember this, is 7.35 to 7.45. Now let's discuss on the properties of water, its physical and chemical properties. Water is described to have an irregular, slightly skewed tetrahedron with oxygen at its center. So this is the structure of water. So it is irregular, meaning it is not quite symmetrical. It is slightly skewed with tetrahedron shape, and oxygen forms the center of the molecule. It contains one oxygen atom and two hydrogen atoms. It has a 105 degrees angle between the two hydrogen bonds. So this oxygen, okay, this is the center of the atom, oxygen, and the angle between the two hydrogen is 105. So this is a better illustration of that of angulation. When we say dipole, it refers to a molecule with electrical charge distributed asymmetrically about its structure. When you say polar, it refers to one end of a molecule is slightly negatively charged and the other end is slightly positively charged. Just like in magnets, one end of the magnet is negative and one end of the magnet is positive. For water, it is considered to be dipole. Why is it considered to be dipole? Because you have two polar sides. Why is it two? Because since you have two hydrogen ions, that hydrogen ions would comprise of a relatively positive electrical charge, and the oxygen is the relatively negatively charged. Okay, and the another portion of hydrogen is a positively charged side, while the oxygen is a negatively charged side. That is why water is considered to be a dipole substance. The portion near the oxygen atom is slightly negative, and the portion near the hydrogen atom is slightly positive. The dielectric constant of water is 78.5, and according to the Coulomb's law, the strength of interaction between oppositely charged particles is inversely proportional to the dielectric constant of the medium. So what does it mean? If we have a higher dielectric constant, the weaker the force of attraction between charged and polar species. So that is the implication if we have the dielectric constant. And the strong dipole and high dielectric constant enable water to dissolve large quantities of charged compounds such as salt. Since, as what I've previously mentioned, that water is a dipole substance, meaning in its molecule, we have two polar sides. We have a positively charged and negatively charged side. Because of that property, it enables that property of water, makes it a good solvent or makes it a good molecule to mix with other charged substances such as salts, because salts contains charged substances such as sodium chloride. Sodium is positively charged and chloride is negatively charged. So if you mix salt or sodium chloride with water, since your water has a positively charged and negatively charged portion, the positively charged portion of water can bind or can interact with the negatively ion of the salt, which is chloride. Okay? And the negative portion of water, which is the oxygen, can interact with a positively charged ion of salt, which is sodium. So that makes it a good substance for it to be mixed with salts. Now let's move on to the types of intermolecular forces in which, or the intermolecular forces in which water is involved. Now, hydrogen bonds are electrostatic interactions between hydrogen atoms and the unshared electron pairs of the electronegative atoms, such as oxygen and nitrogen. Okay, please do take note that this is just an electrostatic interaction. When we say electrostatic interaction, it refers to the attraction of a positively charged and a negatively charged, just like in magnets. Okay? This is in contrast to covalent bonds. When you say covalent bonds, these types of bonds involve actual sharing of electron shells outside of the atoms. And that creates a stronger bond between the two atoms. But for hydrogen bonds, it is just an electrostatic interaction, meaning one portion of the atom is negatively charged, and if you have another molecular atom, one portion is positively charged. Since they have opposite charges, they tend to attract to each other. And that is also the same principle for hydrogen bonds. So it is just an electrostatic interaction between hydrogen atoms. The hydrogen atoms would have a positively charged or a slightly positively charged. And it can interact. Okay, they can interact electrostatically like a magnet with another electronegative charge. Since hydrogen is positive, then it must be attracted to a negatively charged atom such as oxygen and nitrogen. Now, oxygen and nitrogen are electronegative atoms. They are electronegative because they contain an extra electron in which that is found in their outer shell, but the hydrogen doesn't get its electron. It just attracts it. It gets attracted to it because of the opposite charges, just like your magnets. Now, hydrogen bonds are weak, transient, and half-life of and have a half-life of a few picoseconds. Water molecules self-associate with itself via hydrogen bonds. So between water molecules, the reason why they can bind to each other or they can interact with each other is because of these hydrogen bonds. Now, hydrogen bonding profoundly influences the physical properties of water and accounts for its relatively high viscosity, relatively high surface tension, and a relatively high boiling point. So it's because of the hydrogen bonds that it is capable of having a high viscosity, a high surface tension, and high boiling point. On average, each molecule in liquid water associates through hydrogen bonds with 3.5 with each other. Okay, so one molecule of water can bind to 3.5 water molecules. Hydrogen bonds, as what I've mentioned, it's weaker than covalent bonds. Why? Because it is just an electrostatic interaction. Because in covalent bonds, there is actual sharing of electrons, meaning one atom shares an electron with another atom, and it creates a stronger bond. Compared to it, if it's just an electrostatic interaction, just because of the positive and negatively charged attraction, which makes them interact with each other. Hydrogen bonds require 4.5 kilocalorie per mole of energy to break a hydrogen bond. Okay? So it requires this amount of energy to break a hydrogen bond between water molecules compared with the 110 kilocalorie moles to break the covalent bond of a hydroxyl bond within the water molecule. Remember, water is made up of two, hydrogen and oxygen. If you break the oxygen and hydrogen portion or the bonds of water, you need around 110 kilocalories of energy to break them apart. But in hydrogen bonds, you only need 4.5 kilocalories. So it is much weaker. Okay, so let me go back. So this is the structure of the water. This is the chemical structure of water. Again, oxygen is bonded to hydrogen. And this is not a hydrogen bond. This is a covalent bond because hydrogen is actually sharing an electron with oxygen and vice versa. Hydrogen bonds occur when a hydrogen that is already bound to oxygen is electrostatically attracted to the other electronegative atoms such as oxygen. Okay. So any molecule that is capable of hydrogen bonds can do so with water. So for example, of the functional groups that can form hydrogen bonds with water are the aldehydes, ketones, amides, alcohols, and amines. Water is an excellent nucleophile. When you say nucleophile, these are chemical species that forms bonds with electrophiles by donating an electron pair. Why does water has the capacity to donate an electron pair because oxygen has two extra electron pairs. So oxygen atoms of phosphates, alcohols, and carboxylic acids, the sulfur of thiols, nitrogen atoms of amines, and imidazole ring of histidines are electrophile. They are attacked with the oxygen of water. The water, though, specifically the oxygen of water is the nucleophile. Now, when you say hydrolysis, this is the nucleophilic attack by water resulting in cleavage of amide, glycoside, or ester bonds that holds the biopolymers together. And proteases are enzymes that catalyzes the hydrolysis of proteins into amino acids, and nucleases are enzymes that catalyzes the hydrolysis of phosphodiester bond in DNA and the RNA. Now, again, proteases, these are just enzyme that catalyzes or that helps in carrying out this hydrolysis reaction, and nucleases are enzymes that help carries out the hydrolysis reaction. Interaction with water influences the structure of biomolecules. Now we have four major biomolecules. We have carbohydrates, proteins, lipids, and nucleic acids. So these are the four basic major biomolecules in biological systems. And all of these four interacts with water in several ways. The first is through covalent and non-covalent. It can be through covalent and non-covalent bonds. And these bonds stabilizes the biologic molecules or the biomolecules. As what I've previously mentioned, covalent bonds are the strongest force that holds molecules together because it is involved in the actual sharing of electrons of one atom to the other. When we say non-covalent bonds, it only contributes to the stability and functional competence of molecules, and they do not involve actual sharing of electrons. Again, when you say covalent bonds, it is the type of bonds that involve the sharing of electrons between two atoms. The biomolecules fold to position polar and charged polar groups onto their surfaces. Now, most biomolecules are amphipathic. When we say amphipathic, are you familiar with amphibians? Examples of amphibians are frogs, right? So frogs can live in water and they can also live in land. So that is also similar to biomolecules. When you say amphipathic, it possesses both charge or polar region and a hydrophobic region, meaning it contains a hydrophilic portion and a hydrophobic portion. When you say hydrophilic, it loves water. The other synonym of hydrophilic is polar or charged. Hydrophobic is the water-hating region. It hates water. So it shies away from water. And proteins are examples of biomolecules that are amphipathic. Proteins fold with hydrophobic side in the interior because we have amino acids that are hydrophobic. So amino acids that are hydrophilic. Now, hydrophilic or polar amino acids or amino acids with polar side chains are present on the outside in contact with water, and amino acids that contain non-polar side chains or the hydrophobic amino acids tend to shy away from water. So for example, this is a protein. This is a membrane protein. Now, the one that is facing outside the cell or inside the cell, or the one that is in contact with water, that is the hydrophilic portion or the polar portion or the charged portion of the protein. Why? Because it is only this portion that can interact with water either through hydrogen bonds, through electrostatic interactions, while the hydrophobic portion, since it is a non-polar portion, it shies away. It tends to be away from water. Okay? Another application of this amphipathic biomolecule nature in which is in relation to interaction with water are the phospholipid bilayers, which are the major composition of our membranes or the cell membranes. For a phospholipid bilayer, this is the usual structure. So we have the structure of a phospholipid. The the phospholipid head and tail. We have a head and a tail. The heads of the phospholipid layer or the phospholipids contains a charged group, contains phosphate and glycerol. These two would consist of the hydrophilic portion or water-loving portion of the molecule. And why is that? Because it contains charges, which charges and atoms that are capable of forming hydrogen bonds. Now, the tail portion of the phospholipid is considered to be the hydrophobic tail, okay, meaning it shies away from water. Okay, so because we have a hydrophilic portion and a hydrophobic portion, the hydrophilic portion or the polar portion or the charged portion is in contact with water, while the hydrophobic tail is situated away from water, or it excludes water. Okay, and this phospholipid is arranged in such a way wherein the phospholipid bilayer is like this. We have two layers, the upper and lower portion. Each of that portion contains a phospholipid. And as you can see here, the red dots here, these are the hydrophilic portion, and the yellow ones that you see here are the hydrophobic portion. So these red portions are in contact with water, while these yellow ones are away from water because they are hydrophobic. Okay, and what is the reason why it is arranged in this way? This pattern maximizes the formation of energetically favorable charged dipole, dipole-dipole, and hydrogen bonding interactions between polar groups on the biomolecules and water. So this pattern will allow the formation of the bonds that we have been mentioning. And it also minimizes the energetically unfavorable contacts between water and hydrophobic groups, because hydrophobic portions or hydrophobic groups, when it comes contact in water, it is very energetically unfavorable, as we can see later. Now, hydrophobic interactions, this is different from hydrogen bonds, okay? When you say hydrophobic interaction, it refers to the tendency of non-polar substances or non-polar compounds to self-associate in an aqueous environment or in an environment with water. So for example, if you put oil in water, the interaction between oil molecules or the molecules between fats or oils, that is hydrophobic interaction. And when you say self-association, it minimizes the disruption of energetically favorable interactions between the surrounding water molecules. Now, I know that you've been seeing this one. We have carbon that is bonded to hydrogen, and this is very common in 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 your organic chemistry. You have this is methylene groups or methyl groups. You see carbon that is bonded to hydrogen, but this carbon bonded to hydrogen do not participate in hydrogen bond formation. They do not participate in hydrogen bonds in water. Also, in this portion, the hydrophobic tails are made up usually of carbon and hydrogen. But that hydrogen is not capable or are not capable of forming hydrogen bonds because there's no dipole properties. There's no positively portion and negatively portion, meaning it's just neutral. Okay, but this hydrocarbon, it's called hydrocarbon because it just contains hydrogen and carbon. They can affect the structure of the water that surrounds them. The water molecules adjacent to the hydrophobic groups are restricted in the number of orientation, meaning it can restrict the degrees of freedom that permits them to participate in the maximum number of energetically favorable hydrogen bonds. Now, we have been mentioning about the angles of water between between hydrogen atoms of water. That can be disrupted if it is adjacent to a hydrogen or a hydrocarbon. And if that angle is disrupted, it can also affect its property on forming hydrogen bonds. So it can also, it's energetically unfavorable to interact water with a hydrocarbon. The maximal formation of multiple hydrogen bonds, which maximizes enthalpy, can be maintained only by increasing the order of adjacent water molecules to decrease in entropy in disorder. Now, I know that you are familiar with the laws of thermodynamics, and let's just have a review so that you can understand this property. The second law of thermodynamics states that the universe always tends towards increasing disorder. And in all natural processes, the entropy of the universe increases. When you say entropy, this is the degree of disorder or the state of being disorder. So in any natural process, the entropy of the universe increases. The second law of thermodynamics is applicable also in terms of the hydrophobic interactions with water. Optimal free energy of a hydrocarbon water mixture is a function of both maximal enthalpy from hydrogen bonding and the highest entropy, which is the maximum degrees of freedom. Thus, if we have non-polar molecules or hydrophobic molecules that are mixed with water, for example, if we have water and oil, non-polar molecules such as oil tend to form droplets that minimizes exposure of the surface area and reduce the number of water molecules whose motional freedom becomes restricted. And this is applicable for micelle formation. So if you have aqueous environment in the living cell, the hydrophobic portions of biomolecules tend to be buried inside the structure of the molecule or within the lipid bilayer, minimizing contact with water. So a good example is that if we emulsify or if we try to mix water with oil, if we mix water with oil, okay, what happens is that it will self-associate with each other. The oil molecules will self-associate with each other, and it will make a way that the outer portion of that oil, since oils are made up of fat or phospholipids, the outer layer of the phospholipids, these are the charged group or the polar group, that is the only portion that is in contact with water. And all the hydrophobic portion or the non-polar portion will self-associate with each other. The next type of interaction or intermolecular force that water is capable of forming with is the electrostatic interactions. And these are the salt bridges, also known as salt bridges. These are electrostatic interactions between oppositely charged groups within or between biomolecules. And it is comparable in strength to hydrogen bonds, but act over larger distances. The next is the van der Waals forces. Van der Waals forces arise from interaction between transient dipoles generated by the rapid movement of electrons of all neutral atoms. They are significantly weaker than hydrogen bonds, but potentially extremely numerous. So van der Waals forces are actually quite numerous compared to hydrogen bonds. And they act over very short distances, typically 2 to 4 Armstrong. So this illustration shows how van der Waals forces are produced. Okay, so electrons move randomly around an atom, and sometimes more electrons end up on one side of the atom than the other. When close to a second atom, the other atoms would also have a positively charged, and it will create that um, transiently positive and transiently negative portion of the atom. So again, when a close when a sec when when an atom, since Okay, let us start from the beginning. We have electrons moving randomly around an atom, right? Now, there are some times that electrons would end up one side of the atom. When close to a second atom, since you have a slightly negative portion here, it will repel the electrons here and will push it to the other side. And the empty portion with no electrons would have a slightly positively charged. So it will create that transient interaction between the two. It will create a transient electrostatic interaction between the two because you have a slightly positively charged and slightly negatively charged. Okay, so that is how van der Waals forces are produced. And it is very numerous. It's quite numerous compared to hydrogen bonds. The strength of the van der Waals interactions varies with the distance, or R, between interacting species. So this graph shows you here in the y-axis, this is the interaction energy, okay, or the strength of the van der Waals interaction, and the x-axis shows you the distance between interacting species or interacting atoms, okay, and that is measured through Armstrong. The force of interaction between interacting atomic species increases with decreasing distance between them until they are separated by the van der Waals contact distance, which is letter A. The repulsion due to interaction between electron clouds of each atom or molecule then supervenes. And while individual van der Waals interactions are extremely weak, their cumulative effect is nevertheless substantial for macromolecules such as DNA and proteins, which have many atoms in close contact. Now let's move on to dissociation of water. Water can reversibly dissociate into a hydrogen ion or a proton. Okay, hydrogen ion is also known as proton, and a hydroxyl ion or the OH negative. So an alternative description is given in this equation. Water can dissociate into hydrogen plus hydroxyl. Let's now move on to the concept of pH. And pH is introduced by 1909 by Sorensen. And pH is defined as the negative logarithm of the hydrogen ion concentration. Therefore, pH depends on the proton concentration of a solution or the hydrogen ion concentration of the solution. The value is known as the power of hydrogen. So P is the one that is P stands for power of hydrogen. Now, how do we calculate pH? So in calculating pH, we need to calculate the hydrogen ion concentration and calculate the base 10 logarithm of hydrogen ion. And the pH is just the negative value found in step 2. So for example, if you have pure water at 25 degrees Celsius, the hydrogen ion concentration of water is around 1 times 10 raised to the negative 7. And we can calculate it to pH using the equation pH is equal to the negative log of hydrogen ion concentration. Now, why do we need to convert it to pH? Okay, because basically pH will tell us the relatively the concentration of hydrogen ion. Now, why not report it like this? We need to report hydrogen ion in pH because it's very tedious to read this one. You see the value is so small. So we need to convert it to a value that is manageable to read, that is convenient for us to read. A low pH value of less than 7 implicates that it has a higher concentration of hydrogen ion concentration, and it makes the substance or the compound acidic. A high pH value, which is more than 7, has a relatively lower concentration of hydrogen ions, which are considered to be bases. Okay, but the definition of acids and bases are based on several scientists. We have the Arrhenius definition, the Bronsted-Lowry, and the Lewis base. The Arrhenius definition is the narrowest and the most common definition of acid-base. When you see acids, they are substances that produce hydrogen ions in water. So if you put it in water, they can provide or they can produce hydrogen ions in water. They can provide protons. Bases are the ones that produce hydroxyl ions in water. For the Bronsted-Lowry definition, which is the broader definition, acids are substances in which they are proton donors, while bases are proton acceptors. The Lewis definition is the broadest definition of acids and bases, and the definition of a Lewis acid that it is an electron acceptor, and a base is an electron donor. Now, acids are low in pH, meaning they have a higher concentration of hydrogen ions. They are also proton donors based on the Bronsted-Lowry definition. And examples of strong acids are hydrochloric acid and sulfuric acid. They completely dissociate to anions and cations even in strongly acidic solution. Now, we have also weak acids such as albumin, phosphate, sulfate, lactate, and ketones, which partially dissociates in acidic solutions. Now, bases have a higher pH, in which they have lower concentration of hydrogen ions. Again, because pH, it's inversely proportional to the level of hydrogen ions. They are considered to be proton acceptors based on the Bronsted-Lowry definition. And we have also strong and weak bases. A strong base, these are substances such as potassium hydroxide and sodium hydroxide that completely dissociates at basic solutions. For weak bases, they only partially dissociate in basic solutions. Now, what is the pH of extracellular fluid? So the pH of the extracellular fluid is around 7.4. And in clinical practice, the normal range of pH, please remember this, you need to memorize this by heart. The normal pH of the extracellular fluid, in which blood is also part of, is 7.35 to 7.45. Again, in clinical practice, the normal range of pH is 7.35 to 7.45. So that is the normal range of pH. We have 7.35 and 7.45. If we have a pH of less than 7.35, that is considered to be as in a state of acidosis. If we have a pH of more than 7.45, that is in the state of being, or that is the state of alkalosis. Again, less than 7.35 is acidosis, more than 7.45 is alkalosis. Now, why pH is so important, especially in clinical practice? Hydrogen ions react highly with cellular proteins and altering their function. So later on, when you study on the proteins and enzymes, levels of pH can greatly affect its enzymatic activity or its protein structure. Avoiding acidosis and alkalosis is essential also for normal cellular function. And causes of acidosis and alkalosis should be determined and treated. So what laboratory examination will show the acid-base status or the pH of the patient? And this is the arterial blood gas. Okay, arterial blood gas is one way of determining body pH. This is a very, very common procedures, especially now in the times of COVID-19, wherein we have a lot of cases of respiratory failure. We perform arterial blood gas to determine the levels of pH. So how do we usually obtain arterial blood gas? We obtain arterial blood gas by extracting blood directly from an artery. The most accessible artery that we can use or that we can get arterial blood from is from the radial artery. Okay, if you notice your wrist, can you please take a look at your wrist? In the radial portion or the lateral portion of your wrist, wherein your thumb is located here, you can feel pulsation. Okay, and that is the radial artery. And it is also that site wherein we collect blood sample for ABG, or arterial blood gas. And other sites of arterial blood gas collection is through the femoral artery and also from the brachial artery. So As long as that it is an artery, then we can um can be we can extract blood from it. What information does arterial blood gas provide about the patient? Now, arterial blood gas can also determine the oxygenation by determining the partial pressure of oxygen, which is the amount of oxygen dissolved in the blood. This is different from oxygen saturation, or the SO2. Oxygen saturation is usually obtained from using a pulse oximeter. I know that you're familiar with pulse oximeter, so that is the device that wherein you put it in your finger. That is oxygen saturation. But in ABG, the one that you obtain in ABG in terms of the oxygenation is the partial pressure of oxygen, or PA2. And that is the amount of oxygen dissolved in blood. Now, ventilation can also be determined by determining the presence of partial pressure of carbon dioxide, which reflects the adequacy of ventilation, and it is inversely proportional to the partial pressure of carbon dioxide. Basically, it determines the amount of carbon dioxide in blood. Okay? And if you have high ventilation, you have a low partial pressure of carbon dioxide. And if you have a lower ventilation, then you have a higher partial pressure of carbon dioxide. What do you mean by ventilation? Ventilation is the exchange of carbon dioxide from the blood outside the lungs, towards the outside of the alveolus of the lung. Remember that we breathe in and out. Now, it's not just oxygen that we take in. We also exhale carbon dioxide. And when we say ventilation, it refers to the exhalation of carbon dioxide. So if you have poor ventilation, just like in a house, if it's not well ventilated, for example, if you fart inside your room and it's not ventilated, what will happen to the fart? The fart will just circulate around the room, right? The room will smell really bad because there's no ventilation. And if you have a good ventilation, if you have a very wide ventilation, then that fart can easily diffuse out from the room. That is also like in carbon dioxide. So if you have poor ventilation, if you have lower ventilation, you have excess of that carbon dioxide within your blood because it is not capable of your lungs are not capable of exhaling out those excess carbon dioxide. The ABG also determines the acid-base status, such as pH, bicarbonate, and the base deficit. So how do we determine the pH? Again, if it's less than 7.35, it's acidosis. If it's more than 7.45, it's alkalosis. What are the normal arterial blood gas values in a healthy patient breathing room air at sea level? So just like you now, if we try to get the your ABG, what would be the normal levels? So these are the values, usual values. The pH is 7.35 to 7.45. That is our range. The PaCO2, or the partial pressure of carbon dioxide, is 35.45. So how do you easily remember this one? It's just the same as that of the decimal values of the pH. So the PaCO2, or the partial pressure of carbon dioxide, is 35 to 45 millimeters of millimeters of mercury. So it's just the same as the decimal value of the pH. The partial pressure of oxygen is around 80 to 100 millimeters of mercury. The bicarbonate levels is 22 to 26 milliequivalents per liter. The base deficit is positive 3 to negative 3. And the oxygen saturation is 95 to 100%. Okay, so what are the things that you only need to remember by now in interpreting arterial blood gas? Okay, again, these boxed values: pH, PaCO2, and bicarbonate. Again, pH is 7.35 to 7.45. PaCO2 is 35 to 45. Bicarbonate is 22 to 26. Please make sure that you memorize this by heart. So how is the regulation of acid-base balance traditionally described? So we can apply it through the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation states that the pH is equal to the pKa plus the logarithm of the ratio of the conjugate base, and the unassociated acid. Okay? And changes in bicarbonate and PaCO2 determine the pH as follows. So the pH is equal to the pK plus logarithm of bicarbonate divided by 0.03 times partial pressure of carbon dioxide. Now, to prevent a change in pH, any increase or decrease in the PaCO2 should be accompanied by a compensatory increase or decrease in the bicarbonate. Okay, so if you have changes in the PaCO2, for example, if you have poor ventilation, you have a higher PaCO2. If you have a higher PaCO2, since your body wants to maintain an optimal pH, your bicarbonate level should also change, should either increase or decrease, depends on if the PaCO2 increases or decreases. So if you have a higher level of PaCO2, your bicarbonate level should decrease. If you have a lower level of PaCO2, your bicarbonate level should increase to compensate and to maintain that normal body pH. So what are the common acid-base disorders and their compensation? So this table shows you the primary disorder, the primary disturbance, and the primary compensation. If it's respiratory acidosis, the primary disturbance is that you have an elevated carbon dioxide, PaCO2. Again, if it's acidosis, you would expect that the pH is less than 7.35. So in respiratory, when you say respiratory acidosis, it's the PaCO2 that is high. Okay, if you have respiratory acidosis, it's the PaCO2 that is high. And based again to the equation Henderson-Hasselbalch, if you have an increase in PaCO2, what would happen? The primary compensation should be you have an increase in bicarbonate. For respiratory acidosis, if you have in respiratory alkalosis, it's characterized of a lesser levels of PaCO2, but a higher pH, more than 7.45. And the primary compensation for that is that if I lower bicarbonate. For metabolic acidosis, if you have a low bicarbonate levels, then your primary compensation is to decrease the PaCO2. For metabolic acidosis, if you have a higher bicarbonate, then you have a higher PaCO2. Again, in respiratory acidosis, your primary disturbance is the carbon dioxide. Your compensation is to increase the bicarbonate. Okay? Remember that think of carbon dioxide as acid. Think of bicarbonate as base. Okay? So if you have respiratory alkalosis, when you say respiratory alkalosis, you have a lower PaCO2, and your primary compensation is to decrease the levels of bicarbonate or decrease the level of the base, because you do not want to have an excess of bicarbonate, because again, bicarbonate acts like a base. So you do not want to aggravate the further alkalosis. So that is your compensation. Your body needs to compensate the levels of the base. If you have a metabolic acidosis, when you have metabolic acidosis, you have low levels of bicarbonate. So think of bicarbonate again as the base. You have as a base. So if you have a low basic substances, then you need also to decrease the acidic substance such as carbon dioxide. If you have metabolic acidosis, but metabolic alkalosis, in metabolic alkalosis, you have higher levels of bicarbonate. And again, think of the bicarbonate as alkaline or basic substances. So your body needs to compensate it through the carbon dioxide to increase it. Okay. So how do we interpret arterial blood gas? The first is you need to look at the pH. If the pH is less than 7.35, that is acidosis. If the pH is more than 7.45, that is alkalosis. Okay. And if the pH and the other parameters within the normal range, then acid-base disorder is not likely present. So if you check the pH, for example, if the given result is 7.38 and the PaCO2 is 38 and the bicarbonate is 24, What is the interpretation? Again, what's the normal value for pH? It's 7.35 to 7.45. For PaCO2, what's the normal value? It's 35 to 45. For bicarbonate, it's 22 to 26. So all of these three are within the normal range. So therefore, this is a normal acid base. So no acid base disorder that is present. So for this one, you have a pH of 7.21 and a PaCO2 of 35 and a bicarbonate of 18. Okay, so here you see that the pH is low. So if the pH is low, what does that mean? Okay, it's acidosis. Okay, how about the PaCO2? Is it normal or not? Again, what's the normal PaCO2? It's 35 to 45, so this is normal. For bicarbonate, what's the normal level of bicarbonate? It's 22 to 26, so it's low. Okay, so that is acidosis, but we are not sure if this is really respiratory or metabolic. So later on we'll determine. But first, in order for us to determine if it's acidosis or alkalosis, we check for the pH. For this one, 7.50 pH. So the 7.50 pH, this is, since the level is more than 7.45, this is alkalotic. Now second, look at the CO2 and the bicarbonate levels. Remember that the normal CO2 is 35 to 45 and the normal bicarbonate is 22 to 26. If the CO2 is less than 35 or more than 45, that is respiratory. If the bicarbonate is less than 22 or more than 26, that is metabolic. Okay? If the derangement is in the carbon dioxide, that is most likely respiratory. If the derangement is through the bicarbonate, it is most likely metabolic. Okay? So, for example, here, the pH is 7.22, the CO2 is 50, the bicarbonate is 26. The pH is 7.22, so is that acidic or basic or alkalinic? Okay, this is acidic because the pH is less than 0.35, 7.35. How about the PaCO2? The PaCO2 is 50. What's the normal level again of carbon dioxide? Is 35 to 45. So it's high. So this is high. How about the bicarbonate? The bicarbonate is within the normal range. So what type of acidosis are we dealing here in this case? This is respiratory acidosis. Since you have a derangement of the carbon dioxide which is above 45, so that is respiratory acidosis. Okay. Again, take a look at take an example from this one. So if you have a pH of 7.29, so is that alkalinic or acidic? Okay, again, this is also acidic. The PaCO2. The PaCO2 is negative 35 to negative 45. How about the bicarbonate? The bicarbonate is 18. So bicarbonate is lower. So what type of acid-base disturbance are we dealing here? Okay, we are dealing here with metabolic acidosis. Okay, this is metabolic acidosis because PaCO2, if the PaCO2 is decreased, it should reflect a higher pH. Because remember, PaCO2 or carbon dioxide is acidic. It contributes to the acidity of the body. So if you have a lower PaCO2, you wouldn't expect to have an acidotic pH. But since you have a bicarbonate that is very low, and if you have a low bicarbonate, and bicarbonate is like base, so it contributes to the acidity. So the 7.25 acidity is due to the low levels of bicarbonate. Okay, again, think of the carbon dioxide as an acid. Think of a bicarbonate as a base. Okay, the two of these are low, below their normal values, but you have an acidotic pH. Now, between the two, which would contribute to the acidity? Since you have a low PaCO2, meaning you have a low acid, meaning it doesn't contribute to this one, to the pH. But you have a low bicarbonate of a low base or a low base that would actually contribute to being an acidic environment. So this is a metabolic acidosis, acidotic picture of the ABG. How about this one? You have a pH of 7.50 and a PaCO2 of 30 and a bicarbonate of 21. Okay, again, you have a pH of 7.50 and PaCO2 of 30 and a bicarbonate of 21. So what will you check? First is the pH. The pH is alkalinic. Right? The pH is alkalinic. Okay, alkaline. Remember, this is alkaline. You have a PaCO2 or acid. Okay, that's the acidic substance. The bicarbonate, which is the basic substance. Let's see the levels of PaCO2. The PaCO2 is 30. So that is less than less than 35. For bicarbonate, it's 21. So what is bicarbonate? It's less than that of the normal value. So what is this, respiratory or metabolic? Alkalosis. Since this is alkalosis, more than 7.35. So is this respiratory or metabolic? Okay. So for this one, this is respiratory alkalosis. And why is that? Think of again PaCO2 as acidic. Think of bicarbonate as the base. Okay. Your levels of acid or PaCO2 is less than that of the normal value. So that is the one responsible for creating that alkalinic environment. And your bicarbonate is low, 21, because this is the basic substance. Your body is trying to compensate with the low levels of PaCO2. Since you do not want to increase this bicarbonate because you have lower levels of CO2, then your body must make sure that bicarbonate levels should also be decreased in order to maintain a homeostatic environment. So for this one, this is respiratory alkalosis. How do we know that if it's compensated or uncompensated? For compensated, if the value of the pH is within the normal. If the pH is not within the normal level, that is uncompensated. Okay, so for this image, you have a pH of 7.35, PaCO2 of 35, and bicarbonate of 20. The pH is normal. Okay, and PaCO2 is 35. The bicarbonate is 20. So this is a case of compensated metabolic acidosis. Why? Because first, you need to check if the value of the pH is leaning towards the acidity or alkalinity. So 7.35 is around, is at the edge of the acidic pH. It's less than 7.4. And PaCO2 is 35. Okay, that is the cutoff, 35 to 45, and the bicarbonate is 20. So the 20 bicarbonate, that is the one responsible for the low pH. Okay, again, because if you think of the CO2 as acid, think of the bicarbonate as base. So if you have a low basic level, low bicarbonate level, that contributes to the acidity. So that is metabolic acidosis because you have a low bicarbonate and your PaCO2, even if it's just a normal level, it's already at the cutoff. So since you have a normal pH, that is a compensated metabolic acidosis. This is not a normal ABG because one of its component is deranged. So another example of ABG interpretation is this one. If you have a pH of negative 7.55 and PaCO2 of 46 and bicarbonate of 30, you check the pH. Is this acidic or alkalinic? This is alkalinic, so this is alkalosis. You check the PaCO2 and the bicarbonate level. So the PaCO2 is 46. What is 46 for PaCO2? It's high, but it's alkalinic, right? The pH is alkalinic. And if you have a high CO2, you are expected to have an acidotic pH, right? For your bicarbonate is 30. So what is 30? Is that high or low? Since the normal value of bicarbonate is 22 to 26, that is high. So it is metabolic because this bicarbonate is responsible for creating that alkaline pH. So this is metabolic alkalosis. But what type of metabolic alkalosis is it compensated or uncompensated? This is uncompensated because your pH value is not around the normal values. It's beyond 7.45. And take a look another this example. You have a pH of 7.31, PaCO2 of 50, and bicarbonate of 27. First, you need to check the pH. The pH is 7.31. Since it's below 7.35, that is acidosis. Next, you check the PaCO2 and the bicarbonate. Again, you think of the PaCO2 as acid, the bicarbonate as base. So, which of the two is contributory to the acidity? The PaCO2 is 50, so that is high, while the bicarbonate is also high. So which of the two is responsible for creating the acidic pH? Since, again, PaCO2 is acid, bicarbonate is base, so it's the PaCO2 that is responsible for creating the acidic environment. So that is respiratory acidosis. You have a problem in CO2, that is respiratory. If you have a problem with bicarbonate, that is metabolic. Since the one that is responsible for the acidic pH is PaCO2, this is respiratory acidosis. Now, what type of respiratory acidosis? This is uncompensated because your pH value is not within the normal range. So what are the causes of metabolic acidosis and metabolic alkalosis? Metabolic acidosis may be due to ketoacidosis, lactic acidosis, toxins such as methanol, ethylene glycol, salicylates, uremia, diarrhea, renal tubular acidosis. You need to memorize this one. What are the causes of metabolic alkalosis? Vomiting, primary aldosteronism, milk alkali syndrome, and the sodium bicarbonate dialysis. For respiratory acidosis, what are the usual causes? You have CNS depression, such as your anesthetics, neuromuscular blockers, COPD, or chronic obstructive pulmonary disease, sepsis, malignant hyperthermia, and hypermetabolic states. For respiratory alkalosis, the usual causes of respiratory alkalosis are hyperventilation syndrome, or those patients having high respiratory rate that can actually contribute to respiratory alkalosis, pain, and anxiety. Now, buffering is the ability to resist a change in pH following addition of a strong acid or base. And it is very important to maintain pH and prevent acidosis and alkalosis. That's why we have normal buffers in our body. So what are the major buffering systems of the body? You have the bicarbonate, albumin, intracellular proteins, and phosphates. And what organs play a major role in acid-base balance? You have the lungs, kidney, liver, and GI tract. The lungs increase or decrease ventilation to compensate for the metabolic disturbance. For kidneys, the kidneys eliminate fixed acids, control elimination of electrolytes, bicarbonate, and water. Now, the reason why we have high and low bicarbonate is due to the actions of the kidney. And the reasons why we have a high or low PaCO2 is because of the actions of lungs. The liver is also responsible for metabolism of acids, and the GIT is responsible for secreting acidic solutions. What are the major consequences of severe acidosis if you have a pH of less than 7.20? It can cause impairment of cardiac contractility, and therefore will impair the cardiac output, or the amount of blood that is pumped per minute. It can also cause arrhythmias and can lead to a fatal type of arrhythmia called ventricular fibrillation. Can lead to hypotension or low levels of blood pressure. It can cause increased pulmonary vascular resistance, confusion, obtundation, and coma. It can also result to insulin resistance and hyperkalemia, or high levels of serum potassium. What are the major consequences of severe alkalemia if you have a pH of more than 7.60? It can result into increased cardiac contractility until pH is more than 7.7, when a decrease is seen. It can also result into refractory ventricular arrhythmias, coronary artery vasoconstriction. Okay, what will happen if you have coronary artery vasoconstriction? Your blood supply to the heart will be impeded. So you have a problem in supplying blood to the heart. So it can cause myocardial ischemia, or there will be poor perfusion to the heart. So that is also fatal. Can also result to decreased pulmonary vascular resistance. In contrast to severe acidosis, it can result to increased pulmonary vascular resistance. For severe alkalemia, we have a decreased pulmonary vascular resistance, and it can result to hypoventilation. So that ends my lecture on water and pH. So thank you very much for your time and attention in this lecture. So please read the book for more details on water and pH, and try to solve problems in calculating and interpreting ABG. Thank you everyone, and stay safe.